Let's continue with the chapter 6.7.2, that is the sample and hold. The sample and hold behavior must be replaced in my analog system by a block because my simulation program doesn't know anything about a sample and hold block. But you will see the result is very, very simple. But the way to this result is not so simple. So let's first start to understand the behavior of a sample and hold block. In simple things, we can say a sample and hold can be understand like a switch and a capacitor. If this is the input voltage, we can say the output voltage with index H. If the voltage where the switch is closed very shortly, each sampling time shortly, and loads the capacitor to the actual value of U, and then switch is opened and there is no any change of this. So in total we can for example look on a sinusoidal curve which is sampled with the sample and hold block. I have displayed in my workbook, in my paper of this lecture. Look on page 17. There I have this diagram, and I try to explain this diagram in short words. You see here a time diagram. Here was second, here's horizontal grid up to 6 seconds. I sample with half a second, and the black curve is the input of my switch and capacitor sample and hold block. Yeah, the black curve here goes up and down. Ignore at this point the blue curve. Then the output of my sample and hold is the red curve. Here I sample the point. This voltage is held. New sample, holding, new sample, holding, new sample, holding, and you see the black curve is caused by this sample and hold block converted into the red curve. Wow. The resulting red curve now is a base for my digital system. To show you in a quick explanation the main behavior of the sample and hold block, look for the receiver of the digital signal, the red curve. If you want to try to reconstruct the original black curve, what can you do? You can just filter the harmonics away and get the base curve of the red signal, and the base curve is drawn here with blue color. You see that is nearly in the middle of the red curve appears the base frequency of my rectangular red curve. If I filters away all harmonics of the red curve, finally I get back the blue curve. And if I shift now back to the black curve and compare the blue curve with the black curve, you can see there is a delay. And this delay is estimated here very easily with, look on the black curve. The black curve touches always the top left corners of the red curve, and the blue curve lies in the middle of the red curve. And you see the difference is just half a step, and one step is one sampling time, so the difference is then very simply said is half of the sampling time. This can be proven with mathematical calculations. So I now go into the frequency domain and give you some hint for the sample and hold block. We estimate a delay of half of the sampling time seen at the curves in papers. Curves in paper. But now we want to look on the transfer function, frequency domain equation of a sample and hold block. In books you can find that the sample and hold transfer function is 1 minus e to the power of minus p sampling time divided by p sampling time. Now that is the transfer function of this ideal system. And I want to have the frequency response equations of this transfer function. So we can come to the frequency response by replacing p with j omega sampling time. Sorry, with j omega. Yeah, p replaced with j omega. Then we get the frequency response. F of sample and hold. Sorry, my index here is misleading. Of course, I have a sample and hold transfer function. So the frequency response. So the response of sinusoidal signals of the sample and hold block then is 1 minus e to the power of minus j omega sampling time divided by j omega sampling time. This expression has a magnitude and a phase. Let's look at the result. With, you see, e to the power of j, a value can be converted with Euler into sinusoidal and cosinusoidal functions. If you replace this, 1 minus cosinus can be replaced with trigonometrical equations, and with some intermediate steps I want to skip now. The final result is interesting. The final result is a magnitude factor and a phase factor. The magnitude factor is function sinusoidal omega t sub o half value divided by omega t sub o half multiplied with e to the power of minus j omega sampling time divided by 2. So this is the magnitude and this is the phase expression. So the trick here, the 3 points between this factor and this factor have the goal that I want to separate the magnitude behavior and the phase behavior. First look to the magnitude behavior. If we draw the f sample and hold magnitude over log, not over log omega, I want first start with linear omega. Then we start with 0, and you know, look for this. This is a sinus x over x function, the SI function. This has a following behavior. The amplitude goes down linearly with omega. Look for the denominator. Omega is in the denominator. So the amplitude, this is the amplitude factor, goes linearly down with omega. Then we have zeros, that are the zeros of the sinus function. And there is a special case in the near of omega goes to 0. Then we have the ratio 0 divided by 0. But if you solve this with Dubital equation, then the final result is a 1. Yeah, the magnitude of small frequencies is 1. That means, in other words, note the sample and hold block, if you sample fast enough, covers the input signal with the output signal. Yeah, that means if that's a signal frequency, and omega, if this is small signal frequency compared with the sampling frequency, we are here in this region. Yeah, but then now the SE function goes back to 0, and then there are other zeros, but the amplitude then goes smaller and smaller. That is the typical curve of an SI function. Note there is a first zero. Let's calculate the value for the first zero. That is the zero of the sinusoidal function. There we have zeros where omega sampling time divided by 2 is, there is a zero of the sinus function at 0 itself, then at pi, 2 pi, 3 pi, so of an integer number n times pi. And the first zero is n1, so we can calculate omega 0. Omega 01 is 2 times p divided by sampling time. So this is omega 01. What is this for a frequency? The f01 frequency, that's a radian frequency, the frequency itself has to be divided by 2 pi, is 1 over sampling time. This is the sampling frequency. Omega 01 is the sampling frequency, and there we have a 0. That is very easily to understand. If sampling frequency and signal frequency are identical, I get 1 point of each period of a signal, and then the output is 0. Okay, so far that is a magnitude curve. Now have a look on the phase curve. Phase of sample and hold is, the e to the power of j factor is a phasor of a complex number. If you compare with a delay, you will see what is the result. The delay has f delay omega, which is constant 1 times e to the power of minus j omega t delay. And sample and hold, see above, sample and hold has a magnitude, which we have discussed here, magnitude without magnitude bars is magnitude FSH mag multiplied with e to the power of minus j omega t sampling time over t0. Compare the phase factor. You see j is the same, omega is the same, but here this is the delay time and this is the time of my sample and hold. So if you compare this phase of sample and hold is exactly equals phase of a delay time of half of the sampling time. That's what we have guessed here in our first discussion. So what we can say is the sample and hold block, sample and hold with the sampling time sub O, can be replaced by a new block, really a delay time block with a delay of half of the sampling time, and here we have SH magnitude. How can we now work on with our SE function? Very simple. Control systems work in this region because in that region sampling time is too small against my signal frequencies. Here we have the normal area of closed loop systems. Or in other words, the phase shift here is so large that we cannot ignore this phase shift, and then the sampling time is just too large. Yeah, so we can say in closed loop systems we can very easily, without any big problems, replace our sample and hold block with a simple delay time block with half of the sampling time as delay time.